Good morning, everybody. This is a live severe weather briefing as it looks like another active pattern ahead for this week, beginning Monday night with a nocturnal severe weather event across portions of western and central Oklahoma, ejecting off to the east into the Missouri Bootheel region, far northeastern Arkansas, western Tennessee, and Kentucky by Tuesday afternoon. And then it looks like another big system coming in around the Thursday to Friday time period. But this is definitely the first focus right here. This is Monday night. It's going to be associated with a big time jet streak that is ejecting across the southern plains. Here you can see the jet streak at 500 millibars right there. And that creates a jet circulation. Whenever you have these jet streaks like this, the exit region and the entrance region are associated with uplift. In the case of the jet exit, you get uplift in the left exit region. And in the case of the entrance, you get uplift in the right entrance region. And these jet circulations can get coupled with surface pressure falls and can be associated with enhanced wind shear. They can accelerate the low-level jet in the vicinity of the exit region. And this jet streak is arriving late tomorrow night. It should initiate storms at around midnight across western Oklahoma, and those could move in to central Oklahoma, including the Oklahoma City area, late night, probably after midnight. And really this jet circulation is what's going to sustain surface-based storms throughout the night despite the development of low-level convective inhibition. And we're going to be plotting photographs during this live stream as well. Those photographs will be for late Monday night near the Oklahoma City area. We'll assess the tornado potential and the thermodynamics that are limiting factors for that overnight severe weather event, or at least tornadoes. I do think that severe weather, the probability is quite high in Oklahoma for that late night severe weather. The threat of tornadoes, though, is pretty low, and that's because of the low-level stable air that will often build in the middle of the night due to the development of a nocturnal inversion. But still, I do think that with this jet streak, that jet streak circulation that's going to couple with surface pressure falls and enhance that low-level jet, I do think that there is a non-zero tornado threat across central western Oklahoma tomorrow night. And then on Tuesday, that ejects off to the east. Here is the threat. Tuesday, this is the target area. Across an area that has been impacted quite a bit by severe weather this season, the Missouri Bootheel, far northeastern Arkansas into western Tennessee, western Kentucky. Here you can see the trough axis swinging in. And this is a very fast-moving system, so we call that progressive. It is a pretty fast-moving system, but usually these progressive systems like this are associated with these jet streaks. And again, that jet streak will be punching into the Missouri Bootheel region. The left exit of that jet will be right across this region, right in the central Mississippi River Valley into western Tennessee, possibly into central Tennessee, central Kentucky. Once again with this system, that's going to be during the day on Tuesday, the afternoon, and during the evening. For that severe weather threat, that's the same system that is going to lead to potential severe weather on the southern plains tomorrow night. And now I'm going to go through the models really quick, and then we'll be plotting photographs. Here is that system just off the coast of California this evening. This is the system that we're watching for Monday night. You can see some strong flow located on the southern, southeastern part of that trough. And without the big flow on the backside of this trough, this system is no longer digging by this evening. It's already beginning the process of shearing out, even when it's off the coast of California. And that's why this becomes such a progressive, fast-moving system. We go forward another 12 hours. This is Monday morning, and you can see the stronger flow is moving rapidly off to the east through the southwestern U.S., and that will overspread the southern plains by Monday night. But because this system has a weakness of flow on the backside already, it's already starting to flatten out, shear out just a little bit on approach to the southern plains, and that's why we're calling this such a progressive upper level storm system. And that jet streak is moving quickly, overspreading the southern plains by evening. This is Monday mid-afternoon. Monday evening, here is the parent system already really sheared out. Look at how flat this wave is already by Monday afternoon at 4 p.m. Central Time. But you still have that stronger flow, 60, 70, 80 knots here with that strengthening jet streak at the 500 millibar area. And it's that jet circulation that is going to help to initiate storms, help sustain those storms, and potentially, if they can develop long-lived mesocyclones, there's a chance that they could even drill through that stable air. So this time right here, this is Monday morning, early Monday morning at 9Z, and you can see the jet streak has definitely overspread the southern plains, including most of Oklahoma. It still has a defined trough axis, even though it is shearing out. You can see a bit of a subtropical connection. Here's the next system off the coast of California that we're going to be watching for the Thursday time period. It has quite a bit of an energized southern branch that is acting to enhance cyclonic vorticity curvature at the base of that trough, causing this trough to dig. And that's why I think that this next system on Thursday is going to be a higher amplitude trough, whereas this one is a flat, sheared out, progressive type of a storm system. Let's look at the dew points for 9Z. So this is at like 2 in the morning, 3 in the morning. And by 3 in the morning, Monday night, early Tuesday morning, Oklahoma City, at least according to the NAM, has a dew point in the mid-60s. As we'll see on the sounding, this is pretty shallow moisture, dry air just above that inversion that builds in, but still, it's squeezing out mid-60s dew points at the low levels. Here you can see that instability axis materializing in the middle of the night. And if the timing of this progressive jet streak were just during a more of a peak heating time during the diurnal cycle, there is a decent chance that the severe weather could be more substantial. But now I'm going to plot a hodograph for central Oklahoma. I'll show you really quick what the low-level jet looks like. Look at this robust low-level jet that's coupled with that jet streak with the jet circulation. You have some low-level pressure falls in association with that left exit region. And you've got a low-level jet that intensifies above 50 knots here across central Oklahoma tomorrow night at about 2 to 3 in the morning. And I'm going to now plot a hodograph for that location. There is our trusty hodograph, blank plot looking down on the atmosphere. And I've got the NAM forecast wind profile at the bottom right, just below my head there. And we're going to plot this hodograph to try to provide a better understanding of the wind shear that can lead to tornadoes and also hodographs. Hodographs are a great way to visualize the atmosphere. You're looking down on the atmosphere. Here's the origin. So if you have a calm wind, it's at the origin. This is the magnitude of the wind. These concentric circles here, 10 knots, 20 knots as you go out. And wind speed can be plotted based on, it's plotted as a vector. So it has a magnitude and a direction. So these numbers right here are the magnitude, 10, 20, 30. And look at this as just a blank piece of graph paper. But this is just an elegant way of looking at the wind shear. You're looking down at the atmosphere, plotting it. It's a good way to visualize how much wind shear is available for storms to produce. And this right here is the model-derived wind profile that we'll be using to base the plot. So these are the wind vectors with height. This is a kilometer. This is about, or that's the surface. This is about 1 kilometer right here, the next one up. This is about 3 kilometers right here, one up from that. So 3 kilometers, 1 kilometer, near the surface there, near 5 kilometers. And we're going to use this model wind profile to plot the hodograph. You can see there is quite a bit of directional shear with height. You've got a surface wind south-southwest at Oklahoma City at about 3 in the morning. Then you've got your low-level jet just above the ground out of the southwest at 40 knots. And then above 3 kilometers, you've got west-southwesterly winds starting to approach 50 knots. Here you've got that mid-level jet streak that we were talking about. It's in the mid-levels and the upper levels there. The jet streak circulation is usually at the upper levels. The 500 millibar chart that we were looking at is officially the level of non-divergence. But in the left exit region, you get a vacuum cleaner-like effect aloft, and that creates lift through the profile. It's this jet streak that is going to be the main initiating feature to initiate storms overnight. So now let's plot the hodograph and see how the wind shear looks. I suspect since this is the middle of the night, you've got a big wave, or you've got a progressive wave, but a potent jet streak with some low-level pressure falls. I do expect this low-level jet to be quite robust, and we've already seen that in the models. So a surface wind south-southwest at 10 knots. Let's plot that on our hodograph paper here. And remember, it has a magnitude and a direction. So A south-southwest wind is oriented like that. Here's the arrow. That's the vector. Wind speed is 10 knots. So a south-southwest wind, we will plot right about there. That's the dot. That's the surface wind. And now let's go a kilometer above the ground. A kilometer, we've got southwest winds at 40 knots. Due southwest winds at 40 knots. A kilometer above the ground. That's going to be right about there. So the hodograph curve is basically connecting the tips of those vectors. So this vector right here, which is a kilometer above the ground, is south-southwest at 40 knots. This surface wind vector is south-southwest at 10 knots, slight directional shear, quite a bit of speed shear. So when you take one vector and subtract it from another vector, you basically connect the arrow point of the to the arrow point of the vector that you're subtracting from. And that becomes your shear vector. That's the hodograph curve. Let's get a skinnier line here, if I can. So the surface wind, south-southwest at 10 knots. The 1 kilometer wind, southwest at 40 knots. The 3 kilometer wind is west-southwest at 40 knots. So this is the 3 kilometer wind right here. The 5 kilometer wind is west-southwest at 60 knots. So the 5 kilometer wind goes out here. So your hodograph curve, let's connect now the 1 kilometer wind. Subtract the 3 kilometer wind from the 1 kilometer wind from the surface wind. And that's your shear vector between 1 kilometer and the surface. So that's your 0 to 1 kilometer shear vector right there. That's also the part of the hodograph curve. Now we're going to take the 3 kilometer, subtract it from the 1 kilometer. You can do this by a kilometer. You can do it every 500 meters. It's just going to cause your hodograph to be a little bit less smooth if you take these. So here is the 3 kilometer wind minus the 1 kilometer wind vector, and that gives you your 1 to 3 kilometer shear vector. That's the hodograph curve right there. And that aloft, we're accelerating out to 60 knots. And it's these winds out here in the mid and upper levels that really drive the storm motion. They'll result in the storm, they'll be able to bend that storm motion off to the right. They also help to evacuate the rain and the hail from the updraft to keep those mesocyclones sustained, keep them running. So the storm motion, based on the bunker's storm motion here, is 40 knots out of the due west to east. That's basically taking a weighted average of the wind profile experienced by the storm. If you can imagine a big boulder embedded in a stream, the wind is flowing over that boulder. And if that boulder were pretty light, let's just think of a piece of pumice, for example, that floats within the water, and the water flows around that. That pumice isn't going to move at exactly the speed of the water, but a little bit slower than that. But the storm, the motion of that floating boulder through the floating piece of pumice through the stream is driven by an average of the water flow experienced by the entire boulder immersed within that stream. The same goes with a supercell immersed within the wind profile. And usually the mid and upper level flow has a greater weight than the surface winds in driving that storm motion. The bunker's storm motion is just north of due west to east at about 40 knots. I pulled this also from the model derived sounding that I'll show you. So now let's talk about those critical angles. The critical angle is the angle between the tip of the storm motion vector and the surface wind vector, and the 0 to 1 kilometer shear vector roughly. So here is the angle between that 0 to 1 kilometer shear vector and the storm motion vector out here. This angle is the critical angle that we talk about. To really have this most favorable for tornadoes, you want that pretty close to 90 degrees. So you would want to have your low-level jet a bit more backed. And it does look like it is more back to the east of Oklahoma City at this time, more of a south-southwest to north-northeast oriented low-level jet. And if you had a more back to low-level jet or a more southerly low-level jet, then your critical angle is closer to the 90 degrees. And the reason that 90-degree critical angle is so important is because it allows the storm motion to move parallel to those horizontally rotating tubes in the atmosphere that are generated by this wind shear. So imagine a surface wind that's roughly calm, and then the wind just above it at 40 knots out of the due south. You can imagine a piece of paper that's almost calm at the surface. Just above that, you've got a piece of paper moving from south to north at 40 knots. That's going to create a horizontally rotating tube. And in this case, those horizontally rotating tubes are oriented perpendicular to the low-level shear vector between that level. So if you had a storm motion that led to a 90-degree angle with that low-level shear vector, that storm motion is moving parallel to those horizontally rotating tubes. And when the storm motion is moving along those horizontally rotating tubes, it's a lot easier to stretch that horizontal spin into the vertical and develop a long-lived mesocyclone. And one way to quantify the magnitude of the wind shear in the atmosphere is through storm relative helicity. And in this case, that's the area between the hodograph curve and that storm motion vector. It's proportional to that at least. So the greater the critical angle and the longer these shear vectors, the greater the storm relative helicity that you're going to get within that curve between the storm motion and the hodograph curve. So let's see how well we did with plotting this. Let's look at the sounding here. I'm going to take my head off of it just so you can see it better. There's the hodograph at the upper right, and you can see we did a pretty good job. The surface wind in Oklahoma City is just a little bit more out of the due south, and that makes a pretty big difference when it comes to the critical angle. The critical angle in this NAM forecast hodograph is close to 60 degrees. We probably plotted it just a little bit more shallow, and it looks like the 0 to 500 meter winds are just a bit more out of the due south. But look at that dry air just above the ground in on the thermodynamics of the sounding. So here was the hodograph curve. We did a pretty good job. Look at this little loop that it makes between 3 and 4 kilometers. We didn't plot that because we were only plotting the 1 kilometer, 3 kilometer, and 5 kilometer winds. But then above the mid-levels, you get some really strong westerlies aloft, and that's bringing your storm motion back to pretty close to west to east. But we did a pretty good job at visualizing that thing. But look at the thermodynamics of the sounding. You've got pretty shallow moisture. It's late arriving moisture. It arrives in the middle of the night. It's going to be dry, stratiform likely during the day tomorrow, maybe some drizzle developing by evening. But the storms don't really develop until the middle of the night. And you can see quite a bit of dry air coming in just above this inversion. So there is a lot of shallow moisture out there. But if a storm can get going in this environment, there is a chance that if it has a long-lived mesocyclone, it could still drill through this capping inversion. But boy, do these soundings look stable in that layer. Most of these storms are going to be elevated above that cap, beginning up in here, tapping into those steep lapse rates. And most of them will be elevated above that inversion. But if a mesocyclone can get going at this level, one thing that has been shown by these nocturnal jet streaks with late arriving moisture is that they can sustain surface-based mesocyclones despite quite a bit of negative inhibition. And you've got a lot of negative buoyancy between this layer and the lowest 1.5 kilometers with this sounding that it's definitely going to have to drill through. So it certainly is more of a conditional setup on Monday with this event. I'm still waiting on those on the HRRR to see how it handles the convective mode and if it does develop storms in the middle of the night. A lot of times, though, these convective allowing models are not as good with these nocturnal events that have quite a bit of convective inhibition at low levels. You really have to look at the dynamics. You have to break down the jet streak dynamics as well, and just assume that once storms get going, and if they do develop a mesocyclone at about 1.5 kilometers up, there is a chance for that mesocyclone to be strong enough to drill through that convective inhibition and develop a severe weather threat. So then on Tuesday, this system ejects off to the east near the Missouri Bootheel, northeast Arkansas, western Tennessee. Let's break down that setup now, if we can. And that setup has a bit more favorable in terms of the thermodynamics. Again, this is on the Pivotal Weather website, and we're going to have to use. That'll be Tuesday. So here's the setup on Tuesday evening. Let's zoom in a little bit regionally here. Here's that low-level jet that I was talking about, and it's quite a bit more robust during the day. This system on Tuesday is a bit better timed for it relative to the diurnal cycle. This is at 21Z, so 4 p.m. It has the low-level jet axis just to the east of the Mississippi River by this time. By 18Z or 1 p.m., that low-level jet axis is still over the same area. So between 1 and 4, there's not a lot of movement to that low-level jet axis. It does slide just a little bit to the north. That's at 850 millibars. Let's look at the dew points. The dew points are going to be in the low to mid 60s here. There's going to be some funneling of that moisture up the Mississippi River Valley here. But this is more than sufficient for these flat jet streak type setups to get a severe weather threat. And then you still have that moisture feed into western Tennessee, western Kentucky overnight. And there's also a bit of a surface low that ejects through this area that goes from northern Arkansas up across southern Illinois, southern Indiana. And along this surface low track, I do expect some enhanced wind shear right along where the Ohio River meets up with the Mississippi River on Tuesday afternoon. And somewhere along this surface low track, I do expect those surface winds to back just a little bit. You can see how they're more of a southwest to northeast direction across western Tennessee off to the south. So there is going to be some enhanced wind shear near or along that surface low track on Tuesday. And this surface low is going to be pretty close to the left exit region of that jet streak. You basically have a vacuum cleaner evacuating mass aloft in the atmosphere. That leads to surface pressure falls, and that's why you do have this surface low that forms in northern Oklahoma Monday night and then tracks across the Ozarks, eventually near just to the south of the St. Louis area by Tuesday afternoon. And right along that surface low track is where there's going to be some enhanced helicity. This is the 0 to 1 kilometer energy helicity index. Let's pull up the storm relative helicity and look at that helicity that's right in line with that surface low track from southeastern Missouri into far southern Illinois. And there is a little bit of an enhancement in the 0 to 1 kilometer helicity as well to the south of that surface low track. Even with those southwesterly surface winds, you get quite a bit of speed shear across western Tennessee and Kentucky. Still enough to generate well in excess of 200 meters squared per second squared helicities, and you can really see that curved photograph. Interestingly, this system has that little button right there, just a little loop that it makes in the mid-levels of the atmosphere. That shouldn't make a difference because the negative contribution to helicity by this little loop is more than outweighed by the large 0 to 1 kilometer shear vector, with that low-level jet getting up to about 40 to 50 knots. So this is certainly a system that we need to keep an eye out on. Western Tennessee, western Kentucky, the Ohio River Valley there, southeastern Missouri, far northeastern Arkansas on Tuesday afternoon. And then another setup later on, Thursday, a higher amplitude system builds in. So I'm going to now give you one more quick look at the two different target areas. This is Monday night across western and central Oklahoma. There's the jet streak ejecting over the southern plains. And then on Tuesday, this is the target area across the Missouri Bootheel, far southern Illinois. I probably should add far southern Indiana on that as well. Anywhere along that surface low track does have a chance for tornadoes, and that could spread east from western Tennessee, western Kentucky overnight Tuesday night. So now I'm going to go and look at your questions, your comments on the live feed. Thank you guys for joining me. Stay tuned to severe weather during this, and I know that we're socially distancing, socially isolating during this period. So just be sure to hone your severe weather safety plans to also accommodate for that social distancing. And really stay tuned to those watches and warnings during this period, because we are starting to get into the heart of tornado season. Mother Nature is still going to produce tornadoes in the spring and summer, whether there's a pandemic or not, and that's why it's important to adjust those safety plans accordingly. Thank you guys for joining me, and dominate the storm.